Welcome to the virtual lecture for Discrete Math 2 for Tuesday, January 13th, 2015. Similar to the last lecture, this will be broken into several parts. You'll be asked to do some questions on your own and then to check your answers and listen to the solutions if necessary. Part 1 is going to consider section 6.3, Permutations and Combinations. We have already been dealing with permutations and combinations when we learned the product rule, the sum rule, the subtraction rule, and the division rule. We just didn't give them special names. So permutations are ordered arrangements, and combinations are unordered selections. So as examples, a permutation might be the number of ways to place people in a line. There's a first place, a second place, a third place. Combinations are ways to select people to put into a room. There's no order, it's selecting subsets. So do you remember problem 3 from last time where we were counting 3 subsets of a 10-element set? We started by ordering the 3 elements that we were selecting in 10 times 9 times 8 ways. This step is using the product rule to count an ordered arrangement. And at the moment, we're looking at a permutation. But because we're looking for a subset, there's no order involved. Our second step was to use the division rule to divide out by the duplication. This is what allowed us to remove the ordering and then count the combinations. So let's just start with 3 examples, and you decide, is this a permutation or a combination? The number of ways to return graded exams to a class of 14 students. The number of ways to select 3 students in our class to come to the board and solve the same problem simultaneously, and the number of ways to select a president, a vice president, and a treasurer for a club with 14 members. All right, so the first example, the number of ways to return graded exams to a class of 14 students, that's a permutation. There are many ways to order the exams, from highest to lowest, from lowest to highest, or randomly. Usually the students towards the bottom of the stack sweat a little more, so where you're located in the stack seems to make a difference. The number of ways to select 3 students to come to the board, assuming that any spot on the whiteboard is equal. It doesn't matter the order in which those students were selected, they're still the people who are put on the spot. That's considered a combination. And the number of ways to select a president, a vice president, and a treasurer, well, since the title depends on whether they were selected first, second, or third, that is also a permutation. We can actually count these if we want. So the number of ways to return a set of graded exams to 14 students, that is a permutation of all 14 objects. There are 14 ways to select the first exam to go back, 13 ways to select the second exam to go back, all the way down to hand the last exam back. The product of all those, 14 times 13 times 12 times 11, all the way down to 1, is going to be 14 factorial. The number of ways to select 3 students in the same class of 14 to solve the same problem at the whiteboard. We start by selecting the students in an ordered way. That's going to be 14 times 13 times 12. And then we divide out by the repetition. In this case, there are 6 ways to reorder 3 students. So we will divide by our 6 from the 6-legged cow. The number of ways to select a president, a vice president, and a treasurer. Well, there are 14 ways to select the president. There are 13 remaining ways to select the vice president, and 12 ways after that to select the treasurer. So here's our official definition for a permutation. A permutation of a set of distinct objects is an ordered arrangement of these objects. If there are R objects being ordered, we call this an R permutation. The notation we use is P of nr, and this counts the number of R permutations that can be created from an n-element set. The formula we can figure out by applying the product rule. We have to select R objects, and there are, in this case, n choices for the first position. There are n-1 choices for the second position. There are n-2 choices for the third position. We end up with n-r-1 choices for the rth position. If you distribute the negative sign here, you would end up with that final factor as being n-r plus 1. So P of nr can be computed through the formula n times n-1 times n-2, product all the way down to n-r plus 1. I like to think about it this way when I'm creating the permutation step by step. Some people want a nice closed formula. To do that, you can realize you could continue the product here all the way down to 1 as long as you divide by whatever factors you multiplied by. So if I divide and multiply by n-r, n-r minus 1, all the way down to 1, we're multiplying a form of the number 1, but it makes our numerator becomes n factorial and our denominator becomes n minus r factorial. So some people prefer that particular formulation for P of nr. For the parallel definition of combination, you should know that a combination is an unordered selection, and if the number of elements in the subset being selected is R, we're going to call this an R combination. It's denoted by C of nr, sort of parallel to the P of nr we saw previously, or we have this, it's called n choose R. It's also sometimes called the binomial coefficient. Cow counting is what we're going to use to compute n choose R. And to do that, we first start by making the ordered selection. It's going to be the ordered selection of the R sets divided by the number of ways that set of size R could be ordered. Those are the legs of our cow in cow counting. So the numerator ends up being the permutations of n things taken R at a time, and the denominator we're dividing out by R factorial, the number of orderings of R objects. If you don't like this formulation, you can replace the permutations of n things taken R at a time by the formula we just came up with, n factorial over n minus r factorial. And when you simplify, you get n factorial all divided by n minus r factorial times r factorial in the denominator. C of nr is read as combinations of n things taken R at a time. You might ask, why is n choose R called a binomial coefficient? And I hope that you remember the binomial theorem. If you have two real numbers x and y and some positive integer, when we look at the expansion of the binomial x plus y to the nth power, we learned a formula which was a summation as k goes from 0 to n of n factorial divided by n minus k factorial times x to the k, y to the n minus k. Notice the coefficient here, n factorial over n minus k factorial times k factorial, is precisely n choose k. So the coefficient in the binomial expansion is called the binomial coefficient. You might remember that the binomial coefficients can be found by looking at Pascal's triangle. So the rth row here, if I look at the fourth row here, this tells me what the coefficients would be for x plus y to the fourth power. I consider the first row, the top row here, I consider the 0th row, the first row, the second row, and so forth. So if I wanted to write out what x plus y to the 4th would be, I use the coefficients based on the row in the expansion of Pascal's triangle. So I get 1 x to the 4th, 4 x cubed y, 6 x squared y squared, 4 xy cubed, plus 1 y to the 4th. So with that as a background, I want you to test your understanding by computing for me 3 coefficients of binomial expansions. I recommend that you hit pause and then check your answers with mine. All right, let's see how you did. For this first problem, we want the x to the 27th y to the 5th coefficient in the expansion of x plus y to the 32. So that's going to be, well, 27 plus 5 is 32. That's good. So we will be in the situation where k equals 27, n minus k equals 5, and the coefficient of x to the 27th y to the 5th will be 32, choose 5. This is the same as 32, choose 27. When you did the second problem, at issue here is you don't simply have a variable x and y involved, you have 2x minus y. So you will want to break this down. You will think of the first term being added as the entire term 2x and the second term as being negative y, and now apply the binomial theorem to pick off the right coefficient. In this case, we will still have 32 choose 5 as the coefficient, but we're raising the first term, which is 2x, to the 27th power, and the second term, which is negative y, to the 5th power. So we really do have to pull out 2 to the 27th and negative 1 to the 5th. Well, negative 1 to the 5th is negative 1 times 2 to the 27th times 32 choose 5, and that ends up being our coefficient. For the final one, the coefficient of x to the 15th y to the 16th, notice if you add 15 plus 16, you end up with 31 and not 32, so this was a trick question, and the coefficient is 0. And finally, we have 3 practice problems that I'm going to start the next video with. How many bit strings of length 12 have part A, exactly 5 zeros, part B, more zeros than ones, part C, at least 10 ones, part D, at least 3 zeros. Problem 3, how many ways are there for 10 women and 6 men to stand in a line so that no 2 men stand next to each other? And problem 3, it really should say problem 3 there. How many ways are there for those 10 women and 6 men to sit around a circular table so that no 2 men sit next to one another? When you're finished trying these problems on your own, please go to the next video to find the answers.